Here we begin a lesson on the physical properties of alkanes, and we will end the lesson talking about the reactions most common to alkanes. And what are those physical properties of alkanes? And we're looking at a slide that discusses those. Of course, the most important property of an alkane and the cycloalkanes is their almost complete lack of polarity. These straight chains of hydrocarbons have no area of interest in terms of electronegativity differences. We can even see that if we were to subtract carbon and hydrogen using the Pauling scale, finding an electronegativity difference of 0.4 puts it almost exactly in a nonpolar region. So the bonding between a carbon and a hydrogen is almost equivalent, a very even shared pair of electrons. Given that very small difference, we do indeed classify a carbon-hydrogen bond as nonpolar. So knowing that our solute rules say likes dissolve likes, these hydrocarbon chains are nonpolar and will dissolve in nonpolar solvents. Because of the carbon chain, the alkanes here, and later we'll learn alkenes, alkynes, their only type of intermolecular attraction are known as London dispersion forces or simply dispersion forces. Just to review those van der Waals collectively, all molecules exhibit dispersion forces, but those are the only type of intermolecular attractions exhibited by nonpolar. If indeed the molecule is polar, likes dissolve likes, we would have a dipole-dipole interaction. And of course, the strongest of all intermolecular attraction between molecules in this collection called van der Waals forces is the hydrogen bond. But a hydrogen has to be attached to a fluorine, an oxygen, or a nitrogen to meet that criteria of hydrogen bonding. This compound, of course, does not. Hydrogen is bonded to a carbon, making it a very nonpolar structure. When we consider melting points and boiling points of alkanes, they are indeed much lower than those of almost any other type of compound of the same molecular weight. Because of its nonpolar nature, there are very weak intermolecular attractions. So it doesn't take much energy at all to convince the molecule to turn from a liquid into its gaseous state, a very low boiling point. In general, both boiling points and melting points increase with increasing molecular weight. We understand that to be true for just a typical dispersion force trend. The longer the chain we have for our hydrocarbons, the longer the chain means increasing number of N groups for that carbon, the more surface area we have on the molecule, and that greater the surface area as it becomes interacting with the second molecule of the same type, that greater surface area sets up this potential for that temporary induced pole in which a dispersion force is defined as. So the longer the carbon chain, the greater the dispersion force. And so since it is typically the only type of intermolecular attraction, we see that the boiling point and melting point actually increase with that length of the chain because the dispersion force increases. The heavier the molecule becomes, the more energy it takes to separate those molecules from the liquid to the gaseous form. And this indeed is provided for evidence here in this chart called Physical Properties. It is table 11.4 in our chapter 11. The one hydrocarbon chain called methane, molecular weight 16, boiling point of negative 164. Add one more carbon and the boiling point goes to negative 188, a significant increase as we head towards zero, almost half. Propane, adding another carbon, negative 42. Butane, approximately 0 degrees Celsius. But what we're noticing here is the length of the chain. As it increases, the boiling point will increase as well. And that is simply due to the increased intermolecular attractions of the dispersion forces. The longer the carbon chain, the more room those molecules have to interact. The surface area that comes into contact between molecules causes a greater intermolecular attraction. Therefore, the energy needed to break those attractions increase, and therefore the boiling point would increase. Along the same lines, we've discussed this in an earlier course as well. In dispersion forces, the molecular shape of the molecule also plays a role in those intermolecular attractions. For instance, both of these compounds, hexane, C6H14, and 2,2-dimethylbutane, C6H14, they both contain the same number of carbons and hydrogens, but what we notice is that they are indeed arranged in a different geometric fashion. A straight chain hydrocarbon such as hexane, and I say straight chain because there's no branches, even though I know there are bond angles there, but it has a boiling point much higher than if we start to branch those chains, those same 6 carbons but arranged in 3-dimensional fashions, a little bit different bonding order, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane, or 2,2-dimethylbutane, are all different geometric arrangements of the same molecular formula. But make an observation with me. What do you notice about the boiling point as we begin to increase the number of chains, increase the crowding of those alkyl functional groups? Well, of course, you see a drop in the boiling point. The longer, the straighter the chain, such as hexane, when they interact with molecules just like it, there is an increased surface area for one molecule to interact with the other molecule. But if I start creating branches, such as a methyl group coming up or another, like in the middle here, coming down, or increasing yet ever increasing number of branches as we move from left to right in this picture, the opportunity for one molecule to interact with the other molecule decreases, simply because these branches prevent the second molecule, from ever even getting close enough to create a temporarily induced pole. So the more and more branches we have, the less chance you have for molecules to interact and set up a dispersion force. Therefore, lower dispersion forces lowers the boiling point. It doesn't take as much energy to cause a branch chain to boil. There's not as many intermolecular attractions to overcome, and the liquid will turn to the gaseous phase quite readily. The more branches there are in the chain, the fewer the dispersion forces, the lower the boiling point. When we say likes dissolve likes in chemistry, it's a chemist's little tool to remember. Polar will dissolve polar, nonpolar dissolves nonpolar, but never the two shall mix. Because alkanes are not soluble in water, water of course we know to be a polar solvent, alkanes are typically classified as nonpolar, especially the longer the carbon chain becomes, the more nonpolar they act. They are unable to break apart any type of solvent interactions with the water, and therefore they will not dissolve. Nonpolar dissolves nonpolar, so one alkane will dissolve quite readily into another alkane, but not into the polar solvent water. Alkanes are soluble in only nonpolar solvents, such as toluene, diethyl ether, or whatever other nonpolar molecular compound. There's a table 11.4 they have us look at during our reading. The 11.4 table is telling us a little bit about density. It says the average density of a liquid alkane listed in this table, and again that was just this previous slide, bottom of page 340 if you're looking for that very table, is about 0.7 grams per mil. 0.7 grams per mil is the average. The higher the molecular weight, the more dense they become. Just kind of a trend there you can pull out. All liquid and solid alkanes are less dense than that of water. If you recall, water has a density of 1.00 gram per mil, and therefore, because these alkanes are insoluble in water, and they have a density smaller than that of water, they will actually float on the surface of water. So you'll just see two immiscible liquids. Water would sink to the bottom, and you would have the fluid of the alkanes sitting on the top, just similar to like oil and vinegar, oil and water. One will float on top of the other. Let's talk about the reactions of alkanes, the section on 11.9. And we see that there are going to be two main categories that are discussed. That pattern of chemical reaction called combustion, and the pattern of chemical change known as substitution, in which we're going to label halogenation, taking a halogen and replacing a hydrogen with one of our group 7A elements known as halogens. Well, let's begin discussing combustions. Any type of hydrocarbon, C something, H something, where those somethings are called subscripts, when they combust, they ignite, we burn those fuels, and we always have the same skeleton in our pattern. You add oxygen. Remember, anything that is burning requires oxygen. That little triangle, remember the arrow represents heat. Anything that is burning requires oxygen, and a complete combustion is going to produce carbon dioxide and water, and a very exothermic value, heat releasing, simple burning of natural gas called methane. We probably heat your home with natural gas. Methane is the simplest of all hydrocarbons, releasing 212 kilocalories of energy per mole of fuel burned. Now, propane is what we use in our gas tanks when we're lighting our gas grill outside. Commonly, people will have a propane tank. Propane, C3H28CH3, when it combusts, we add oxygens, out comes carbon dioxide and water. That longer hydrogen chain, you can see a greater release of heat. So again, remember, every time you're breaking a bond, that's an energy releasing formula. So the longer the chain, the greater the amount of energy that is indeed released. Octane, C8H18, is a fuel commonly found in gasoline. We have octane ratings, if you will, in a gasoline. And again, remember when you're trying to balance these, the trick here we learned in an earlier course is start with the C's, then the H's, then the O's. So a combustion is an automatic pilot in terms of balancing. Add oxygen, produce carbon dioxide and water. The heat of reaction will always be an exothermic value. Remember here, this is shown as products, but you could also see that as delta H equals negative 530 kilocalories per mole. The negative sign on a heat of reaction is showing us an exothermic heat releasing. But this particular chapter represents that as as a product. Products are being produced. Energy that's produced means exothermic. Its delta H value is indeed negative. Back to this example, when we balance this equation, I'll start with my carbons, balancing those first. Then I move to my hydrogens, balancing those next. 18 H's, 8 carbons, and I'm doing this on purpose to remember our old adage of double the odd number problem, because right now I have 16 O's coming from the CO2, 9 coming from the water, giving me a remainder here of 25 for the total value of oxygens. Well, there's no way I can have 25 oxygens without a fraction here. So the old trick is to say everything you just fixed, double the fuel, and you can get that to balance quite readily. So the coefficient here would become 2, 25, 16, 18 for that complete combustion of a fuel called octane, the main ingredient, of course, in gasoline that we place into our car engines to get them to go. So an oxidation, better known as a combustion, oxidation means to add oxygen. The familiar pattern of combustion from inorganic chemistry, take a hydrocarbon and ignite it, means add oxygen, out comes carbon dioxide and water. A second type of reaction discussed in our chapters is that with a halogen. These are those elements found in group 7A. Fluorine, bromine, chlorine, iodine, those halogens are found in group 7A. When we think about halogenation, it's a simple substitution. It occurs one step at a time. Take a simple methane molecule, CH4. CH4 reacts with a halogen, such as chlorine. Halogens could be fluorine, chlorine, bromine, or iodine. Those elements found in group 7A on your periodic table. All of these collectively are known as the halogen family. Chlorine belongs to the halogen family. When I take molecular chlorine and react it with a great deal of heat or light or some sort of impetus, some sort of activation energy to get the reaction to go, we'll break one hydrogen off and replace it with that halogenated chlorine. Notice that we get HCl as the other product. This hydrogen is cleaved off and replaced with one of the chlorines. If we continue this step in a step-by-step fashion, this product becomes the reactant in the next step. Methyl chloride plus another molecular chlorine will give us dichloromethane. Now we've replaced two of the chlorines. We replaced two of the hydrogens with chlorine, and so forth. If you continue treating with increased heat and light, you can replace the third hydrogen, and ultimately the fourth hydrogen is replaced. But a step-by-step process of halogenation. Not all at once. If you see CH4 plus Cl2, you've only received one chlorine onto the methyl group. So, we're looking at examples. Well, let's put a little example in here. Write a balanced equation. This is looking at page 344, example 11.9. Write a balanced equation for the reaction of ethane, CH3, CH3, with chlorine to produce chloroethane. Now notice these are all hydrogens. This molecule we just created, C2H6, is called ethane plus molecular chlorine. Only one of the groups, one of the hydrogen will be cleaved off and replaced with the hydrogen. And again, these two ends are created equal, so it wouldn't matter here, but just keep in mind it's a one-step substitution. And now this other hydrogen goes to the chlorine. So this single bond for chlorine, single bond chlorine, this is a bond that breaks. This is a bond that breaks. One of the chlorine attaches to this site, and the hydrogen attaches here. So a substitution reaction in this halogenation. The hydrogen carbon bond breaks, the chlorine to chlorine bond breaks. We substitute onto the carbon chain the chlorine, and that cleaved hydrogen will go to the other chlorine from the molecular form of chlorine here, a diatomic molecule. So here's our formula, or our compound, called chloroethane and hydrogen chloride. And again, I would assume this is a gas, so I won't name it as an acid. Hydrogen chloride is a gas. The reaction of propane, CH3, CH2, CH3, the molecule called propane, reacting with chlorine. And it's going to give us two products, each of with the molecular formula C3H7Cl. Let's draw the structural formulas for these two compounds and then give the IUPAC name for the common Oh, we could give a common name too, it says. So again, here's just pulling from our chapter 11, 344 is our page. This is problem 11.9, kind of in that yellow box in the center. Propane plus molecular chlorine, Cl, single bond Cl. We have two different arrangements now for this propane molecule. It will be called propyl chloride, just as this was called ethylene chloride or so forth. So ethyl chloride, here the IDE ending as it attaches. So we could have an arrangement. Let's just kind of play with this. We have 3 carbons in a row. That's the propane root word. Where might we place that single chlorine? Well, one of the attachments might be at the terminal end. The molecular formula becomes C3H7Cl. To name this with the IUPAC name, remember that the hydrocarbon right here gets the number 1. So we would call that 1-chloropropane. Alrighty, 1-chloropropane. Or we could call it propyl chloride. This is the IUPAC. This is the common name. Where else might that go? However, if we look at, we put it at the terminal end, what about there in the second carbon? What if we drew that propyl group and put the chlorine there? We still end up with the same structural formula, or the same molecular formula, C3H7Cl, but what about that IUPAC name? We come up with 2-chloropropane. Alrighty, 2-chloropropane or 2-propyl chloride. IUPAC, generally what you're going to end up being asked is the IUPAC name. The common name just kind of lets that halide group kind of become the last name here. 2-propyl chloride says there's a chloride group on a 3-carbon chain. The last section talks about the sources and uses of alkanes. And section 10, what are the most important haloalkanes? It talks about chlorofluorocarbons. CFCs is what they're commonly called. We often hear them trademarked under a name, a manufacturer name called Freon. Freon to me means refrigerant coolant, although it's been mostly replaced now because of the harmful effect on the ozone. In this section, I would say it's a pretty straightforward section. You can pull out any questions you might need to answer from your testing just by simply reading. So it's kind of a nice to know section about sources of alkanes and their uses in the industry, but I won't make us take any additional notes here. It's just kind of an extra nice to know. You'll go ahead and read a little bit about chlorofluorocarbons, and even a little bit about petroleum distillation is discussed in our chapter, a way of taking this crude oil and based on temperature we can start separating out the different kinds of fuels all the way from solid residues up to the highest temperatures possible. The gases start to come out here, and you'll just start to read a little bit about the length of the carbon chain will determine if it comes out as a gas, as a liquid, and eventually out as a solid. And increasing molecular weights, of course, are going to affect the state of matter that it will be separated from. But again, I'll just say all of this is a nice reading material. Congratulations, you've made it through the Chapter 11 set of video notes.